I would like to talk about a minimal U1 extension of the standard model, which can be tested at the future electron-positron collider via the Fermion pair production modes. So we all know that the standard model has been established on a very strong foundation. And a few years back, we observed uh, the Higgs at the Large Hadron Collider, and we noticed that the mass of the Higgs could be around 125 GeV. However, there are a few more interesting things which came in the form of anomalies, that the existence of the tiny neutrino mass and flavor mixing, which was studied by these neutrino oscillation experiments, and also relic abundance of the dark matter. However, we do not know what is which are responsible for these, the nature of the neutrino mass ordering, or what is a potential dark matter candidate. So if we want to explain these things, we cannot do that within the standard model. We need to extend the standard model. So to do that, we try to find a simple scenario where the standard model can be extended by a general U1 group. And in this case, we include three generations of the right-handed neutrinos, which are standard model singlet, and also a standard model singlet scalar in the form of phi. So if we solve the anomalies like gauge and mixed gauge gravity anomalies, we see that the charges of the standard model fermions under the U1x can be written as the linear combination of U1y and U1b minus L. So U1y and U1b minus L are separately an anomaly-free scenario, are the anomaly-free scenarios. So the U1x is also an anomaly-free scenario. So from the particle content, we notice that the neutrino mass can be written in terms of the scalar phi, where the U1x breaking can generate the Majorana mass term for phi nRC bar nr from this term, and then the Dirac mass term can be generated by the first term of this Yukawa interaction. So from this, the seesaw mechanism can be produced to explain the small neutrino mass and the flavor mixing. In addition to that, there is a new neutral gauge boson beyond the standard model gauge boson, which can be denoted as a Z prime. So if we write the Higgs potential, and if we do the U1x breaking followed by the electroic breaking, then we can write down the mass of the Z prime in terms of the U1x wave V phi and electroic wave and the charge of the Higgs doublet. We have kept x phi equal to 1 for simplicity. And if we take the large wave limit, then we see that mz prime can be written as 2g prime v phi. We already have noticed that the neutrino mass can be generated through the seesaw mechanism. So one can study the neutrino, or the effects of the neutrino oscillation and flavor mixing in this model as well. The interesting thing is that the interaction of the Z prime between the left sector and right sectors of the fermions in this model are different. That is due to the different U1x charges of the left-handed charged fermion and the right-handed charged fermion. So that is manifested in these Lagrangians LQ and LL for the quarks and leptons respectively. So you see that this QXLQ and QXRQ, these are the U1x charges of the left-handed and right-handed quarks, whereas QXLL and QXRL, these are the left-handed and right-handed charges of the leptons, respective leptons under the U1x. So next we write down the partial decay weights of the charged fermion, light neutrinos and the heavy neutrinos. So in case of heavy neutrinos, we follow this 1 minus 4 mn square by mz prime square. So if this is not followed, then the right hand, the z prime cannot decay into a pair of the right-handed neutrinos. Another interesting thing is, like, if we fix our x phi at 1 and keep changing xh from -2 to 2, then we see that for xh equal to minus 2, there is no interaction between the left-handed fermions and z prime. If we fix xh at -1, then there is no interaction between the z prime and the right-handed electron. For xh equal to minus 0.5, there is no interaction between the right-handed uptype quark and the z prime. And if xh equal to 1, then there is no interaction between the z prime and the downtype, right-handed downtype quark. So this is a very interesting feature of this model if we fix x phi equal to 1 and keep changing xh. So this model is very interesting because it has a variety of phenomenological aspects, because it has a new gauge boson, that is Z prime. It has the Majorana, heavy Majorana neutrinos. It has the U1x Higgs boson. And this is phenomenologically very rich because one can study this Z prime boson and its decay, heavy neutrino production. Even adding some symmetries or some singlet particles, one can explain the dark matter scenario, collider aspect of the U1x Higgs, vacuum stability, leptogenesis, etc. So in this talk, we will discuss about the fermionic pair production from the Z prime. We see that the electron-positron collider, this FF bar can be produced from the S channel and the T channel. So in the S channel process, if we produce fermions other than electrons, then we only have the S channel contribution. Otherwise, if we produce E plus E minus 2 E plus E plus E minus, E plus E minus 2 E plus E minus, then we'll have the Bhabha scattering at the S channel and T channel processes. So we considered the limits on the model parameters, considering mz prime is heavier than the center of mass energy at the LEP and the prospective ILC. So using the effective theory approach, we can show this limit plot on mz prime by g prime with respect to xh. Mz prime by g prime is nothing but the wave. So the LEP to ILC 250, 500 and 1 TeV can probe this wave up to say 400 TeV or so for the XH less than 0. So when XH is greater than 0, then it can reach up to say 700 TeV or so. We also compared our results with the recent dilepton and dijet searches from the LHC using this master formula. And also this LEP limit can produce, LEP limit and the ILC prospective limits can produce some constraints on G prime with respect to MZ prime. So we see these things for the XH less than 0. We have compared CMS and Atlas dilepton. It's Atlas TDR from dilepton, and also CMS and Atlas DiJet results, which are loose compared to the dilepton searches, also LEP2 and the prospective electron-positron colliders from 250 GeV to 1 TeV. So we notice that this when the Z prime is heavier, then the LHC limits are loose compared to the electron-positron limits, LEP or the prospective ILC searches. So this is the scenario when XH is greater than 0, and the conclusion is the same. So we produce the electron positron to mu plus mu minus and electron positron to electron positron using the Vava scattering. So we see that the deviation can be large. So we find the sharp resonance at the Z prime mass at 7.5 TeV for a different for center of mass energy less than 3 TeV as well, one can have useful deviation or sizable deviation. So we study these forward backward asymmetry from the E plus E minus going to mu plus mu minus at the 7.5 TeV Z prime. So we see that if we study at the 500 GeV collider for XH equal to 2, then the deviation can be 3.8%, whereas for XH equal to 1, this deviation can be 79% at 1 TeV using these polarizations of the electron. And for PE equal to 0.3 at 3 TeV, for XH equal to -1, the polarization can be 20%. The interesting fact actually comes in case of the left-right asymmetry, because the left-handed and right-handed fermions are differently charged with the Z prime. So we see that even at 250 GeV, XH equal to 2, the left-right asymmetry could be, the deviation from the standard model could be 10% for XH equal to 2. And XH equal to 1, the deviation can be 20% for this E plus E minus going to mu plus mu minus channel at 500 GeV. Similarly, at the same center of mass energy, XH equal to -2 will produce nearly 8% of the deviation. We study the left-right forward-backward asymmetry from the electron-positron and electron-positron to mu plus mu minus production. We see that the deviation of this process could be 8.2% for XH equal to 2 at 250 GeV. For XH equal to 1, it could be 15% at 500 GeV, and XH equal to -2, it could be 7.5% at 500 GeV. So this is very interesting because even at the low center of mass energy, such deviations can be observed, and that is not small. That is of the order of like 10% or so. So it will be an interesting scenario to study even at the 250 GeV ILC. So I conclude that we are looking for a scenario where a variety of standard model, beyond the standard model scenarios can be tested. So we have this proposal for the neutrino mass to the seesaw mechanism. We can study the forward backward left right and left right forward backward asymmetries at 250 GeV and 500 GeV electron positron collider, and also in the higher center of mass energy in the near future. Such a model can also be tested at the muon colliders with higher center of mass energies. So this model is very much prospective. So if you want to look at this model and all the detailed analysis, including the Vava scattering, please see this paper. And the motivation of this work is, of course, to study a beyond the standard model scenario, along with some new particle and new gauge boson. Thank you very much for your attention.